what we have here on the screen is a data set with DTPA data, and the purpose of this is to give those of you who want to use Excel some idea of how to analyze the data. So first of all, let's have a look at what we've got in there. We've got some identifying information for each sample. In this case, there are relatively few samples, 27 different observations, geographic data. NA means missing data. Something happened there. We lost the data somewhere. DTPA concentrations, which you measured in a lab, and we'll get your data soon for a bunch of elements, including some which we don't usually measure DTPA concentrations for, such as neodymium, which is one of the rare earth elements, and so on. We've also got some supporting data, and you will be provided with something like this as well. So we've got EC and pH for the soils, and total concentrations of a whole bunch of different elements, some of which will be more relevant than others. Okay, so what I would tend to do is to make a column showing the fractional amount of an element of interest extracted by DTPA. And so the way we're going to do this is to make that column. So let's call it zinc dot percent DTPA. Alright, so we'll make sure we can see everything, and so we need to calculate that. So that would be the zinc concentration measured by DTPA extraction divided by the total zinc concentration at that particular location. Okay, we'll make sure we get the columns right. I just about chose zirconium there. So I'll just leave them as fractions, and let's perhaps tidy that up a little bit. Let's give it a few less decimal places just for tidiness, and of course we can copy that formula down. Now we've got an error value there because there is no total concentration of zinc for that particular sample, so I'm just going to delete that. And in fact, because we don't have total element concentrations for anything in that row, we may as well delete the whole row. Okay, and that's going to make things slightly easier. So now I've got a column of zinc percent DTPA, and what I can do now is a few things based on the data analysis available to us within Excel. And this is assuming, of course, that the computers in our UWA computer labs have got the data analysis tool pack enabled. Let's hope they do. So one of the things that we can do is to look at, so we click on data analysis, and what I'm going to hopefully be able to do is to calculate correlations. Alright, so we get a dialog box opening up, and we have an input range. So I'm going to put my labels in first row, and I'm going to select that input range. And I'm going to look at the correlation of the fraction of zinc extracted by DTPA with just about everything I can get my hands on. And one of the reasons I've used zinc is I need to use a continuous range for the correlation analysis, and I can include, in fact I won't do that. That doesn't make sense. Okay, so we've got a whole lot of potential predictors. Of course, if we had soil organic carbon content in there, that might be good as well. And what I can either select an output range, or I can select a new worksheet, apply, meaning a different page in the worksheet to put the data in. I'm just going to call it corals for want of a better phrase, and I click OK, and it does not like me. Alright, so I've got some non-numeric data. Oh, of course, I've got some NAs in there, which it doesn't like at all. Okay, so I can cancel that, and that these mistakes are actually quite useful because you may run up with these yourself. So I'm going to do a search and replace, find and replace. So Control H, and I'm going to find NO, and I'm basically going to replace it with nothing. Replace all. Okay, and I'm going to try that again. So data analysis stays on correlation. I click OK, and it should save what we put in. And I'm going to try again. So we get a correlation matrix spat out by the data. A little bit difficult for you to see probably because of the zoom level, so I'm just going to make that a bit bigger. And you can see that immediately we've got some indication of the strength of correlation. Unlike a full bottle statistical program, we don't have a statistical test associated with the correlation calculation of correlation coefficient. So we'll need to make some judgment for ourselves based on the R value, which is our effect size, if you like, for the correlation. So what I'm going to do is also view, freeze panes, and freeze the top row so we can see which column that we're looking at. And I'm going to look down at my zinc as a extraction. I'm just going to highlight that a bit so we can see what we're looking at. And I'm going to look for largish positive or negative correlation values there. One way we can do this, of course, is to use conditional formatting. Now, I don't think I can see this on. I can. Okay, so color scale's quite handy, so we'll do that. And what that will hopefully give us is that the large positive values become the brightest red colors and the large negative values become the brightest blue colors, and we flick through to see what we've got. Okay, so there aren't really any high positive correlations. Most of them are negative, which is interesting. So the fraction of zinc extracted by DTPA seems to be negatively correlated to a bunch of things. The point is, do some of them make sense? Let's have a look at some of the higher values. Well, barium, maybe it's a trace element, so that may be somewhat coincidental. And we can fiddle around with our correlation analysis to only include major elements if we wanted to. Cadmium, again, the reason for that is probably zinc and cadmium highly correlated, but here's an interesting one. We've got iron in there, a major element known to affect the chemistry of trace elements in soils and similar materials, and it's suggesting that we have a negative relationship between the proportion of zinc extractable by DTPA and iron. So the more iron in soils, the less proportionally we can extract with DTPA, which kind of makes sense if iron is retaining zinc in a form that DTPA can't access, which is quite likely. So that's why I'd go through it. Manganese doing something similar, and sometimes manganese oxides perform a similar role to iron oxides. That may or may not be the case here. What else have we got in terms of major elements? Silicon. Okay, so that's unusual. That means there's more silicon, which can mean a sandier soil, and also total zinc. So total zinc should have an influence on the amount extractable by DTPA. If the mechanism for zinc retention in the soil is mainly by some sort of adsorption, a surface process, then usually the more zinc we have in the soil, the more available or mobile it becomes, more extractable by something like DTPA, because with large amounts of zinc we have all the very strong adsorption sites occupied, and so the ones left over for the rest of the zinc will be weaker. And so we'd expect to see a positive relationship in that case between total zinc, total metal, and the amount extracted by DTPA. And we see the opposite in this case, suggesting that possibly the zinc is held in different ways, maybe as in the structure of minerals, and that may become more pronounced, we're guessing here of course, as the more zinc we have in the soil. But it's not an unreasonable thing. So the interesting result, what we have here, is the apparent role of iron in reducing extractability of zinc. So that tells us something about how a system's behaving. So we could do the same sort of analysis for the fraction of other elements extracted by DTPA and see if we get any common ground there. So that's something of interest, I think. Alright, so that's correlation analysis. Let's then go back to our data and have a look at regression analysis. So this is where we don't look for relationships, we look for the ability to predict stuff. Now, what I'm going to do here is to create a different list. I'm going to get rid of a bunch of minor elements and relegate them to the back row, so to speak. So there's a whole lot of things that I don't really want. Okay, so now I've got a list of possible predictors for DTPA extractable zinc, or at least the proportion of zinc extractable by DTPA. Okay, so now I've got my list down to a subset of elements that are likely to be able to act as predictors, so mainly the major elements and total zinc that are able to act as potential regression predictors for the proportion of zinc extractable by DTPA, so zinc DTPA divided by zinc total. Alright, so again, we can go to our data analysis tool pack in Excel, but in this case we don't want correlation, we want regression. Okay, so again we get a dialog box. So we get a Y range, and these, this is our dependent variable, and we're going to pick this as being this column here. We want our predictors. Now in the first instance I'm going to just use one. I'm going to use iron just to demonstrate a simple linear regression, and we've got labels. We don't necessarily want at constant 0. We'll put a 95% confidence interval in there to calculate probabilities, and we're going to make a new worksheet ply, and I'm going to call it FE regression. Alright, so do I want anything else in there? Not really, but I might want a line fit plot, and I might want to have a look at the residuals. So we'll see what happens when we do that. Okay, so here are our data, and so we get a bunch of output which we can see a bit more easily if we adjust the width, particularly of the first column. Alright, now first of all, let's have a look at our graphs. Now we've got, first of all, we have some skewed data showing the relationship between, in this case, zinc extractable by DTPA as a proportion of total, and iron total. Okay, now we can see a little bit better what's going on. Okay, so iron total seems to be a good predictor of zinc extractable by DTPA, which we deduced anyway from the regression relationship, but it's always good to check the XY plot in case we've got extreme outliers that might affect the regression procedure. Okay, just make it a little bit bigger again so we can see what we're doing. Alright, and as we saw before with the negative correlation coefficient, we've got zinc extractable by DTPA tending to decrease as the concentration of iron increases. So we have an explanation for that. We've got some statistical testing of the relationship. So here's our significance of our, or basically the probability of getting the relationship that we have got there if a null hypothesis is true. That is, null hypothesis if there's no relationship. Alright, okay, and we have an R² value which is not all that flash, of about 0.3, so say 30% of the variance in zinc extractable by DTPA is explained by iron concentrations. Right, we've got some statistics on our intercept and multiplier for iron. Right. Now, something else that we often do with regression models is have a look at the residuals. Now, this is optional for you. They should be approximately normally distributed with a mean of 0. They probably are, but what we probably ought to have done was to log transform iron concentrations before we did the regression. So we can do that. We can go through and we can log transform anything we like, really, and the more careful of you will be doing that, but we'll get a similar trend. Okay. I would envisage. Don't quote me on that. It's not top quality statistics, but there we go. Okay, so there we go. That's how we do a simple linear regression. Now we're going to go back to our data and go back into data analysis, and you'll see now we've selected regression. We want a range of predictors. Now, at the moment, we've only got iron selected as our predictor range. Let's have a go at using multiple predictors. Let's say everything from EC through the major elements and so on through to zinc total is possible predictor, and they may all act together and simultaneously influence the proportion of zinc extracted by DTPA. Alright, so we're going to do a multiple regression of this. Okay, so here we get one. I'm going to produce way too many graphs, so I'm not even going to look at those. But now we've got a much more complicated result. Okay, so what's interesting here is that the significance of the relationship, so the p-value, which is not a measure of how good our model is, the R² value is, so don't worry about that. It means that at the moment we have we can't reject our null hypothesis that there's no multivariate relationship, but that's probably because we've got too many parameters in the model, and we'll note in a minute that we don't need to use all of them, but we do have a much better predictive ability. So now with that combination of predictors, we can account for about 3/4, our R² value, 3/4 of the variance in the proportion of zinc extracted by DTPA. Alright, now let's look at p-values for each predictor, and you'll notice that some of them have p-values below our 0.05 threshold or 95% significance, and some don't. In fact, none of the individual predictors do, only the intercept at the moment. Now, what would we do here? Now that we can run the model again and weed out some of the predictors that don't seem to give us on the basis of a p-value, basically, or the size of the standard error of the coefficient. That's misleading because we should really use the relative size. So I'm going to focus on the p-value. I'm going to weed out the least significant. Again, that's a bit of a stretch in interpretation of p-values, but we'll go with it anyway. I'm going to weed out total aluminium. It's sometimes a useful predictor because it is aluminium is a proxy for clay content, but let's weed it out. So we would go through a process like this. So we'd go back to our data. We'd find total aluminium, and let's cut that, add it to our big list of rejects at the back, and let's go back and run our regression again. Right, now in this case we need to select reselect the range of predictors, so we're going to go again from EC through to total zinc, but in this case we've got no aluminium in there, so we'll get a different regression. Let's call that multi-regression 2, and so on and so on. Alright. Input range, of course, has shifted, so we need to reselect that. That's because we deleted a column, and we'll... Okay, so multi-regression 2, again with our squillions of graphs. Let's not be too anal about that. Again, we can see that our p-values in our table of coefficients has changed. So now some of them have much lower p-values, but we've still got some which are insignificant. So in this case, we would weed out EC because it has the highest p-value. Okay, so you can go through a process like this until all of the p-values for each coefficient are less than 0.05. And that's I guess a manual version of stepwise regression that a more sophisticated statistical software would do. Alright, so we can do that. So what I've ended up here with is a regression model where all the p-values are significant at a p less than 0.05 level, and I have an R-squared value, which is not too much less than the maximal model that we looked at before, so about 69% of the variance in DTPA extractable zinc is explained by a range of predictors. Now let's go down and have a look at those. So we've got pH, iron, potassium, magnesium, sodium, silicon, zinc. Now you may argue about the significance of including potassium, magnesium, sodium, and it may be hard to assign some real world significance or mechanism to those. Potassium sometimes can represent clay minerals, and as can magnesium, so maybe there's something going on there, but we're a bit of a guess. Sodium could represent the salinity of the system, and again that can affect adsorption reactions, but you know, we're never sure about what's going on there. But all our p-values are significant, and we've got a much lower p-value for our overall regression statistics. So we've got a model now, and the next thing to do is to look at the coefficients. So this block of information here is going to be kind of instructive. All right. So what we're saying is that our proportion of zinc extractable by DTPA in this case decreases as pH increases. Well, that kind of makes sense, because we'd expect more precipitation at high pH, reducing extractability, also more adsorption, so that kind of makes sense. We've now got a positive coefficient, albeit a fairly small one, for iron, so maybe iron is not that important when we have a multiple regression model. Of course, you know, it's a bit of an artwork because it depends on the initial list of predictors that we put in. So obviously iron by itself wasn't a bad predictor, it was the best of the lot. But in combination it has less of an effect. Alright, so pH actually has the largest effect, judging by the size of its coefficient, which makes sense. And some of the other things, so potassium, which might represent clays, the more potassium in the soil, the less the extractability because of the sign, negative sign on the coefficient. Same with silicon, which we saw before, and zinc as well. So the more zinc in the soil total, the less extractable it becomes, which is what we saw from our correlation table previously. So we can go through a rather lengthy process to get a multiple regression model in Excel that makes sense, weeding out parameters as they go. Now, it's not a perfect way of doing it, because if we did a true stepwise procedure, we'd then, with our minimal model, we'd try adding parameters back in. I guess the final thing that we might want to do is to see if there are any variables in our data that could be split up into kind of high, low, or high, medium, low categories, and whether that has any effect on extractability. Okay, so we can have a crack at doing that, and again, the way that we can do that is with our data analysis tool pack in Excel. In this case, we want to run a histogram. I'm just going to run a default histogram here. We're going to call it hist pH because I'm going to run it for pH. Let's choose our input range, which will be our soil pH. We've got to find it somewhere, of course. There it is. Okay, we've got labels at the top of that range, so we better put them in. We don't actually have a range of bins, so we're not going to do that. And we'll have some chart output. We want to actually see the histogram, which will tell us something about distribution. So let's do that. Okay, so never mind the odd position of breaks in the histogram, which is just something that Excel does. So if we delete that and that, Excel's usual chart junk, we can see that there does appear to be a bimodal distribution in pH, which might cross over at about, maybe about 7, okay, just for argument's sake. So what we could do then is we could go back to our data and divide it up. Now this becomes a little tricky in Excel, so let's insert a column and pH class, we're going to call it, and we'll use an if statement. If that number is less than 7, we'll say that it's low pH. Don't forget the double quotes. If it's not, then we'll say it's high pH. Alright, so copy that down, see if it works. Formatting's kind of annoying. We can deal with that, I guess, if we're really fussy about making it look nice, but it doesn't really matter that much. Now, how are we going to do this now? Well, unfortunately in Excel we're going to need to support to sort our data. So I'm going to select that entire range. I'm going to go to data, sort, and I'm going to sort by pH class, right? Now, okay, forgot to do something there. What we need to do now, whether we've established those, is to copy them and then basically paste them as values back onto themselves. Now we can do that. Data sort by pH class, A to Z, and we get some ranges. Now, what we're interested in now, let's make them different colours for argument's sake. Is there a difference between those means? So how can we do that? Well, let's have a look at our data analysis tool, and let's do a 2-sample t-test, assume unequal variances, which is basically our Welch's t-test, and okay, so variable 1 range, this one here, variable 2 range, this one here, hypothesized mean difference, let's say we assume that our mean difference is 0, we don't have labels, we want a new worksheet apply, okay, so, whoops, t-test, and okay, so here it is, and okay, so our t-statistic actually, the p associated with t, or one-tailed or two-tailed p-value, shows that our comparison doesn't show a significant difference between soils of high pH and low pH. Okay, so that's another thing we could do there. And we could potentially have a look at the histogram for iron and see if that's splittable into two classes as well. Or we could just decide what represents high iron and low iron. We have a look at the data, we have a look at iron, we see there's a range of values there, and we say, okay, anything above 10,000 is high iron, anything below is low, and we make a comparison. Okay, same sort of process.